All right, so, whoa, sorry. This collar is too small. Better kill you with my volume. All right, so last time we started, I raced through a bunch of stuff because I wanted to give you a big picture, and today we're going to be more careful. The focus for today is embeddings, which is the idea of placing a set of points into a metric space. In a way that satisfies certain conditions. Okay. And the first embedding that we saw was semi-definite programming embedding. Which we use to embed a graph, or the vertices of a graph. Into a Euclidean space. Such that edge endpoints were far apart, right? We use this in order to generate cuts with many edges. Just to get us warmed up, let me remind you of another embedding that we did, which was to embed a graph in order to find a minimum cut between a pair of vertices S and T. So for this, I defined a different, an LP relaxation of this problem, where we said, let's this time look at the capacitated version, because it's no harder. So we're going to have capacities on the edges, U sub E, or U sub VW. And we are going to want to minimize a sum of indicators that an edge is cut times the capacity of that edge, with the constraint that the indicator variables be between 0 and 1, and also with a cut side variable, a cut side indicator variable, ZV, for every vertex V, which is also an indicator variable for whether it's on the left or the right. And we constrain these indicator variables with this triangle inequality, which says that if you want vertex W to be on the right, so that ZW equals 1, and you also want vertex V to be on the left, so that ZV equals 0, then in order to satisfy this constraint, you have to set YVW equal to 1, which forces that edge, the indicator for that edge, to mean that that edge is cut. Yes? So that's what it is saying in terms of indicators. Oh, and by the way, this works even for directed graphs. We've spent a lot of time on undirected graphs in this class, but this is a linear program that is meaningful for directed graphs. You only count an edge as being cut if the tail is in the left side and the head is in the right side. And then finally, we require that S be on the left and T be on the right. Okay, and so this is an integer linear program that exactly captures the ST min-cut problem. Yes? Any questions about it? Okay. Now, we can't solve integer linear programs, but we can solve the LP relaxation of this integer linear program. As a relaxation, we get a better value, right? So the fractional optimum is no worse than the ST min-cut, right? But this fractional linear program can also be seen as an embedding of the graph G on the line such that S is at 0 and T is at 1. Okay, the Z variables are the position of each vertex on the line. Okay. But the triangle inequality says that the distance between V and W is at most YVW. So we can think of the YVWs are lengths that we are assigning to the edges. And we are then saying that you have to place the vertex, you pick some lengths for the edges, and now you place the vertices on the line so that no edge is stretched beyond its length. Is that clear? Okay. So the fact that this is a relaxation means that it is possible to choose these lengths, right, such that the objective is the sum of y VW UVW, is what you can think of as the volume of all the edges. If UVW, which is its capacity, is thought of as its sort of cross-sectional area. So we think of these edges as pipes, and the capacity of an edge is proportional to the area, the cross-section, the circle that is formed when you cut the pipe, right? You double the area, that cross-sectional area, you're doubling the capacity of what can go through that pipe. Okay? And so we take that cross-sectional area and multiply it by a length that we're assigning, and we get a volume of that pipe. Okay? And so that is telling us that the volume of, the total volume of our graph is no larger than the ST minimum cut, right? Okay. Now we can see this directly if we think about how to take a particular ST min cut and turn it into a solution to the linear program. It's not necessarily an optimal solution, but it is a feasible solution, right? So if you have a particular ST min cut, what solution to the linear program does that correspond to? Remember, an ST min cut is just an integer solution to this linear program, right? So if I have a particular integer solution, what is that doing in this vocabulary? What does it put where? Yes? And where do the vertices go? Exactly, right? It puts the left-hand side vertices at 0, the right-hand side vertices at 1, right? And then it assigns length 1 to all the min-cut edges. It has to, because those endpoints are separated by a unit of distance, right? And 0 to all the others. Yes? So this is just another way of seeing that this LP is a relaxation of ST min-cut, right? Every ST min-cut corresponds to a feasible solution with the same value, right? Since I assigned 1 to all the min-cut edges, the value of the objective is just the value of that min-cut, right? Okay, so this is actually an example of what is known as a cut metric. Okay, you've got 2 sets of points. And if you are on the same side or in the same subset, then your distance is 0. And if you are on different sides, then your distance is 1. Okay? So this cut metric is a special case of a metric on the line, right? But in the fractional solutions, we're allowed to pick a different metric on the line. So we might do better with the fractional solution. But I showed you a rounding scheme last time that demonstrates that actually we don't do better, right? So if we're given a fractional solution, how do we round it? Well, what we described last time is we just pick a random t, or not t. I need a different letter. R, between 0 and 1. Okay. I'm going to make it strictly between 0 and 1 so that S and T are on opposite sides of this R, right? And then I put vertices with ZV less than R go on the left, and vertices with ZV greater than or equal to R go on the right. Okay? I'm simply taking my graph, which has had all of its vertices laid onto the line, and I'm simply picking an R that splits the line and therefore splits the vertices and creates a cut. Yes? So what is the expected value of the cut that I create through this splitting procedure? Well, we take the usual first step, right? The value of the cut can be seen as a sum over all edges of the expected value of that edge's contribution to the cut. Right? Which is just equal to the sum of the probabilities that edge E is cut. So what is the probability that edge E is cut when I pick a random R? Yeah? Not quite. Intuitively, yes, but there's a little bit of slack in the linear program. Yes? Why? So what is the exact value, right? If V is placed here and W is placed here, what's the probability that this edge is cut? I think this question is too easy for you to answer, right? What determines the probability that R separates V and W? Yeah, it's the difference between them, right? So this is the sum of the absolute value of the difference between the endpoints. Yes? Actually, sorry, if I'm thinking about directed edges, then it's just ZW minus ZV. Right, I said this is going to work for directed min cut as well. So, let's stick with X. So what our linear program says is that ZW minus ZV is upper bounded by the edge length, right? Oh, and if it is cut, then it contributes UVW to the value of the cut, right? So this is upper bounded by this quantity, which is equal to the LP optimum. Yes? Yes, thank you. I left this out. Okay. So the expected value of the cut that we get is equal to the value of the linear program. Okay. Now this is actually a little bit weird. Okay. It means that our approximation ratio, so to speak, is 1. Right? Now let's think about divergence from that expectation. Right? Maybe the expected value is 1 times opt, but what's the probability distribution of values that we might attain? Right? So can the outcome be less than the LP opt? Yeah? Exactly, right? The outcome is a cut, and so it is a feasible solution to the LP, right? Which means that the value is always at least the LP opt. Now, if it is always at least the LP opt, then that puts some constraint on how often it can be above the LP opt if we want to have the right, if it's always at least the LP opt, how often can it be above the LP opt if we want to have this expectation? Yeah? Never, right? Any time it goes above, it's contributing, it's pushing you above that LP opt. And there's nothing to cancel it out by going below. So in fact, so we never go above, which means that we don't actually need to pick a random R. Any R will do. All of the R values will give you a ST min cut. Okay. Which almost suggests that you're only going to get integer solutions, but that's not quite true. You can have sort of tight edges all the way along. You can have a vertex, like a very simple case would be a graph that literally looks like this. Okay? The ST min cut of this graph is 1. You can put this vertex anywhere in between, and you'll still get an LP optimum of 1. But it's not an integer solution. So there are these fractional solutions, which are essentially linear combinations of cuts that prevent the LP from always being fractional. But this does show that the optimum of the LP is equal to the ST minimum cut, which means that there are integer optimum solutions. Okay? So this is a second example of an embedding, where instead of embedding into a high-dimensional Euclidean space, we embedded into a one-dimensional Euclidean space. Okay? So the reason I introduced this was because now we're going to do a much deeper dive into embedding with more complex problems. I introduced 3 problems last time. Bisection is the problem of finding a minimum cut with n over 2 vertices per side. I talked about separator. And I'm going to concentrate, the constant doesn't really matter here, but it's just that you want a constant fraction of the vertices on each side. And then I talked about ratio cut, where you want to minimize over all partitions, let's call this S bar, of the number of edges crossing from S to S complement divided by the product of the two sides. Okay? And I'm going to call this the separation of S, and it's the number of edges crossing if G is the complete graph. Right? It's the number of places that you could have an edge that crosses between the two sides. Okay? And I talked last time about how useful this class of problems is for distributing computation over multiple servers. And I also showed a toy example of how you can use it in divide and conquer algorithms for finding approximations to various NP-hard problems. Okay, so there's a lot of motivation for solving this problem. It is solved a lot in practice, and it has also had a very rich theory developed around it. Now, all of these problems are NP-hard. And in fact, we're nowhere near constant factor approximations. What we are going to be developing today is an order log n approximation for separator and for ratio cut. The same techniques can be applied to get an order log n approximation for bisection, but they're messier. So I'm not going to look further at bisection. I'm going to concentrate on these two problems. And the first thing I'm going to show you is how you can use ratio cut in order to get an approximation to separator. And after that, I'll show you how to get a log n approximation to ratio cut. Okay? So one thing to notice about ratio cut is that one of S and its complement is larger than n over 2, right? But less than n. So if we replace the larger of these two by n, we're only changing things by a factor of 2. Right? So we can say that this quantity is equal to theta of crossing edges divided by n times the minimum of the size of S and the size of S bar. Yes? And if we think about, if we ignore this n for a moment and just look at number of crossing edges divided by the smaller side, right? You can think of that as the average degree of the smaller side in terms of crossing edges, right? Agreed? Okay. And this is what I'm talking about here is just how you compute the ratio of a cut. And it doesn't matter if it's the sparsest cut or not, right? I should actually, this is generally called sparsest cut. Ratio is the quantity that we're trying to minimize, but it is sometimes called ratio cut. So basically, to within this factor of 2, which is sort of irrelevant given that we're going for an order log n approximation, what we're trying to do is minimize the average number of edges leaving a vertex to the other side from the small side of the cut. Yes? Okay. So with that in mind, I can now describe an algorithm that uses ratio cut to get a separator with roughly the same ratio, and therefore which can be used to get an equivalent approximation for separator. Okay, let's find my notes again. So here's how we transform a sparsest cut algorithm into a separator algorithm. What we do is, while we have what am I trying to say here? Yeah, while we have more than 2/3 n vertices remaining, I am going to find the sparsest cut, and I'm going to remove smaller side. Yes? Argument. Okay. Yeah, I mean, you can probably get from the ratio to the argument through some sort of self-reducibility, but all the algorithms actually find the partition. Okay. So why does this work? Well, let's look at the analysis. So we're running this loop while we have more than 2/3 n vertices. Okay. Now I'm going to simplify the analysis by assuming that we have a nice bisection of value b in the original. You can work a little harder if you start with a separator of value b, then it takes a little more work, but the ideas are the same. Okay, and you'll see why in a minute. So we had a bisection of value b in the original graph. We've removed at most n/3 vertices, which means that each side of the bisection still has at least n/6 vertices. Yes? If I've got my math right. Okay. So that means that the ratio of the bisection cut in the remaining graph is at most the number of edges crossing the bisection, which is b, divided by n over 6 squared, right? So there is a, actually, let me say it a little bit more carefully. So its size exactly is b divided by the product of the sizes of the two sides that we've taken the bisection of, right? And as before, one of these, the larger one, is omega of n. So we're going to treat it as an n, right? So this is theta of b divided by n times the smaller side, right? But this smaller side is at least n over 6, because that's what's left. Okay. And again, what that means is that when we will find a bisection of this ratio, or we will find a separator with this ratio times whatever our approximation algorithm is, right? The approximation factor is alpha, right? Which means that the quantity that we find, the ratio that we find, will have this value, right? Alpha b divided by n times the smaller side. And again, this quantity b divided by the smaller side is just the average number of edges leaving, right? So this is alpha over n times the average leaving degree of the smaller side of the cut, right? Or, to put it another way, the average leaving degree of the cut that we find will be at most alpha times the optimum leaving degree, or theta of alpha times the optimum leaving degree. Okay, because we are able to approximate to that ratio. Okay, and so we keep on removing basically a set of vertices whose leaving degree is only alpha times the leaving degree of the bisection, right? So this is theta of alpha times the bisection's leaving degree, right? And so we keep taking away vertices and giving them an average degree, which is about the bisection's average leaving degree. Okay. And that means that when we finish, we've done this over and over again, right? And so the collection of vertices that we've set aside have, each time we bring in some new ones, they still have the same average leaving degree, so the entire set will have the same average leaving degree, right? So we're forced to stop, but we don't stop until we have taken away n over 3 vertices, right? So we don't stop until we've removed at least n over 3 vertices in total. Okay. But if you think about it, each step of the loop starts with more than 2n over 3 vertices. And we remove the smaller side each time. Right? Which means that we're always going to be leaving behind at least n over 3 vertices. Right? So we keep on removing vertices. We don't stop until we are below 2n over 3, but when we stop, we are still above n over 3. Okay? So among the remaining vertices, we will have between n over 3 and 2n over 3. In other words, we will have a separator. Right? That's the definition of a separator. But each incremental step gave us an average degree, which is proportional to alpha times the average degree of the optimum bisection, which means that at the end, it will have average degree theta of alpha times the bisections average degree. And that will give us what we want. Is that clear? If it's not clear, ask. Or ask if you care. You can just say, okay, I'm going to ignore that and watch the algorithm for sparsest cut. But if you are interested in how you get from sparsest cut to separator, and this is not clear, then ask. No? We're good? Okay. So the rest of the lecture will be spent on the core of all of this, which is an algorithm for approximating sparsest cut. And I should say, the first algorithms for this were developed right here at MIT by Tom Layton, who's in the math department, and Satish Rao, while he was doing his doctorate here. He's now a professor at Berkeley. But they did it sort of as a one-off, developing a specialized algorithm for this, which, looking back, had these critical ideas in it, but hadn't quite formulated them the way I'm going to be explaining them to you in this language of embeddings. And so I'm going to be showing you this very nice version due to Aman and Rabbani. Which really shows directly how you can solve this problem using embeddings and talks about how to get a good embedding and use it to solve the problem. And it's really connected to the Layton-Rao approach, but it's more transparent about what's going on. So we are going to start, once again, by thinking about a relaxation of the ratio problem. Okay. So first of all, instead of minimizing the ratio, I am going to ask to minimize the numerator while keeping the denominator larger than 1. Okay? We're going to use an LP relaxation. It's going to assign fractional values to things, and we're going to have sort of a fractional value for the numerator and a fractional value for the denominator. But because it's a linear program, you can scale everything, right? You can divide all of the numbers by 3, and you get the same ratio. So we will simply rescale the numbers so that the denominator is 1. And the reason for that is that linear programming doesn't like to divide things, right? Linear programming is about linear constraints. So our relaxation is going to be that, again, we want to assign edge lengths. Okay, this is another cut problem. So again, we're going to be trying to represent the edges in a metric space so that the ends of vertices, so that the endpoints of edges are not too far apart. That's the equivalent of not having a large cut. We are going to do it so that the sum of pairwise distances is greater than or equal to 1. The optimum will set it equal to be 1. It'll make it tight. And the sum of the edge lengths is minimized. Okay. So let me ask, is this a relaxation? Or why is this a relaxation? In other words, is there a way to assign numbers, to assign lengths to the edges such that the value of this ratio is better than the sparsest cut ratio? Well, as with ST-min-cut, all we have to go on is, here is a particular cut that is the sparsest cut that achieves the best ratio, right? So let's consider the S yielding the optimum ratio. Okay. I need to give you a solution to this length assignment that gives me a good ratio. Okay. What I'm going to do is I'm going to assign a length of 1 over S times S complement to every cut edge, and 0 to all the other edges. Okay. Now, right, this is just a defined procedure, right? I've told you what number to put on every edge, right? Now, what can I say about the sorry, I should say pairwise distances of vertices on opposite sides. Because that's all we're counting in the ratio. Okay. So if I do this assignment, what is the sum? What is the denominator? Yeah? Exactly, right? So the denominator is there are S times S prime pairs, right? Sorry, not the denominator, the ratio, right? The sum of lengths, the sum of edge lengths is equal to the value of the separator times the number that I'm putting onto the cut edges, right? Which is just equal to the ratio that I'm interested in. Yes, a question?
Why do we need the condition of vertices on opposite sides?
Because, wait a minute, where did I go here? Yeah, the question is, what is the denominator, right? What did I just mess up here? Pairwise distances. That times the number of cut pairs. Oh, yes, of course. So, no, that's not of course. Pairs. Sorry, I've got, this gives me that the value of the objective function is the ratio that I want. I'm blanking on why it guarantees that the sum of pairwise distances is at least 1. Oh, yes, of course, right? So vertices on opposite sides are separated by the cut. Right? That's the definition. Which means that you have to use a cut edge to get from one to the other. Which means that each pair has distance at least this magic factor. Yes? So for each pair of vertices on opposite sides, the shortest path between them uses a cut edge, and that means that the distance between them is at least this, which means that if I sum it over all of the pairs, there are s times s prime pairs, which means that the sum of the distances is at least 1. Yes? So this meets the requirement. And again, you can scale this if you want to, right? If I instead assigned a value 1 to every edge, then the numerator would be the value of the cut, and the denominator would be s times s prime. Same scaling. So yes, your question? No, it's for this reason, right? The vertices on opposite sides have to, sorry, if the, you're right, it is true that I can look at the sum over all pairs of vertices, but the point is that I get the bound just by looking at vertices on opposite sides of the cut. Everything else might have distance 0, so it doesn't contribute. Okay, so this is an unnecessary but satisfied condition. Does that make sense? Okay. All right. So we know we have a relaxation. I claim I can write it as a linear program. I am going to define edge lengths, just as before, which I will call YVW. I am going to define distances, dVW, more variables, via triangle inequality constraints. I basically say that the distance from V to W has to be less than or equal to the distance from V to X plus YXW, my usual triangle inequality constraint, right? If the D's satisfy these triangle inequalities, then that it follows that these D's are lower bounds on the distances. Yes? Okay, so I can define these distances. Now I just require, so now I can write out my linear program, right? I can say, I'm trying to minimize the sum of dVW times UVW, sorry, YVW times UVW. Again, same as before, total volume of the graph. Actually, the having capacities doesn't change anything, but I may drop them later for if it makes intuitive sense. And then I'm going to require that the sum of the dVWs should be greater than or equal to 1. Right? Sum of pairwise distances has to exceed 1, subject to these triangle inequality constraints. Okay, there's no longer a source or a sink. I don't specify that the source goes someplace or that the sink goes somewhere because there isn't one. I'm just saying that you have to spread out the vertices so that their total distance from each other is large. But you want to minimize the volume of the edges while you're doing that. So ideally, vertices with no edge between them will be very far apart to contribute a lot to the distance, but vertices with an edge connecting them will be very close together so that they don't contribute to the volume. Does that make sense? Okay. So you'll notice that this is another embedding problem, right? This is asking us to define a metric space, to come up with a set of distances between vertices that satisfy the triangle inequality. It's not a Euclidean embedding, right? It's not asking us to, it's not like the semi-definite program which embedded the points in a vector space. It's not like the ST min-cut problem which embedded the points on a line. This is embedding in an abstract metric space where the only thing that is defined is the distances between points. So the points don't have a position. They just have distances from each other. Okay. Actually, I should check. Has everybody seen the definition of a metric space? Anybody want to ask about that? A metric space is just a collection of points with distances between them that satisfy the triangle inequality. So that's what we're creating here. Okay. So we have created an arbitrary metric that is a relaxation of the ratio cut problem, right? We also know that there are these, that cuts are metrics, right? As we saw in this ST min cut problem, right? The metric where you put a distance of 1 between things on opposite sides of the cut, that is a metric, and 0 other, if they're on the same side, is a metric. So what we are going to need to do now is round this arbitrary metric space to a cut metric. All right? And that's what we need to do to finish the approximation algorithm, is figure out what sort of ratio we lose when we round an arbitrary metric to a cut metric. All right? But that's going to take some brain power, so let's take a break first, and then I will show you how to do that.
Is that problem 4C? So 4 is the wiring rooms to routers
Yes.
problem.
Yes.
So I was able to get part B, but I was only able to get my grounding seam to get like LP optimum in expectation. I couldn't
Yes.
get a with high probability.
That's okay. In expectation is sufficient.
For 4C, when it says at cost O of log n times, is that an expectation as well, or does this need to occur with high probability?
Well, so the phrasing is that your cost should be only order log n, but it's okay to wire a constant fraction in expectation.
But I wasn't able to get this to hold with high probability.
Really?
Because basically I run like O of log n iterations of something. Each one has like LP optimum expected cost, but I can't guarantee that it's that cost.
All right,
high
let
probability.
me think about that. I may have to issue an erratum. Okay. I will look that over after class. All right, so now that I've queued up this problem of we want to round one embedding into another, or we want to transform one into another, theoreticians generalized this question. Okay, the general question of embeddings is how well can one metric space be embedded in another? Okay. So if you think about it, what we've actually been doing is, I mean, I've talked about it in terms of embedding graphs in metrics, but a graph is a metric space, right? If you have a graph, right, and you think of each edge as having length 1, then the shortest paths in that graph define a metric on the vertices of the graphs. So when I'm trying to embed a graph into a metric space, I'm really trying to embed a metric into another metric. Okay. So we can talk about an embedding phi from one metric space on points x with a distance d to another metric space, and I'm going to, it's really the same set of points, but with a different distance function on them, is, we call it a contraction if the distance in the embedded space is not bigger than the distance in the original space. So whatever this mapping is of points, it brings them closer together. That's a contraction. Okay. We say that it has distortion C if, as a contraction, the distance in the embedded space is larger than C times the distance in the original space. Okay? So the reason I restrict to contractions here is that, of course, you can scale a metric space, or you can multiply all the distances by 3, which doesn't change anything meaningful. But if you did that arbitrarily, you could make all of the distances in the new metric space bigger by just multiplying all the distances by a large number. But if you restrict it to be a contraction, right, you're not allowed to make anything farther apart. And so with that restriction, right, that you can't make things farther apart, the approximation can be measured by how close together you bring things. Yes? And we call this an isometry. If C equals 1. That just means you manage to get all of the distances exactly right. So are those definitions clear? So now let me point out some basic things about embeddings. So first of all, isometric embedding into the L2 norm. Actually, let me do this. Let me give you some definitions of norms first. So what are some interesting metrics? Well, there's the Euclidean metric, right? The usual sum of square root of the sum of yi minus xi all squared in whatever number of dimensions your space is, right? That's the one that we're most used to. Okay. Now another one is what's known as the Manhattan metric. So the Manhattan metric is basically Manhattan. When you have a collection of points, you're allowed to take a path that has to move only in axis-aligned pieces. So in 2 dimensions, you can only move vertically or horizontally. And so you can see that as the crow flies, right, the distance here is less than the distance that you get if you have to actually stay on the streets of Manhattan. Yes? But it is a metric because it's shortest paths of a certain type, right? So this is just the sum, this is just the sum of the absolute value of the differences in coordinates between the points, right? You have to move on each axis separately, and on a particular axis, the distance you travel is the absolute value of the difference between the coordinates. Yes? You can go this a different direction, or actually, you can generalize this, right? You notice this is a square root of squares. This is a 1th root of 1 powers. You can talk about the LP norm, which is the sum of the pth powers of the differences, all raised to the 1 over p power. Okay? And if you think about it, right, varying p here is basically varying how much attention you pay to large coordinate differences versus small coordinate differences, right? Here, with the absolute values, small coordinate differences contribute just as much as large coordinate differences. When you start squaring, the large coordinate differences really take over and small coordinate differences don't matter at all. As p goes to infinity, what happens? What happens in the limit as p goes to infinity? Yeah? You only care about the largest. And so this is the L infinity norm, which is just the max of the absolute values. Yes? Yes, because you can this can be defined even for non-integer values of p. All right, so this is a collection of norms. And what we're going to see, kind of, is that the bigger p is, the easier it is to embed in an LP norm. So first of all, isometric embedding into L2 is polynomial time solvable. Okay. And I claim that I've already told you how to do it. So this is the normal metric space where points, right, or vectors in Euclidean space, and you're trying to enforce certain distances between the vectors. So, yes. So no, that's what deciding whether it exists is polynomial time solvable. Okay. Well, it's both at the same time, actually. You can find it if it exists, and if it doesn't, then you can say so. Okay. The reason is that distances are basically dot products, right? And we know how to force dot products, right? What we do is I'm going to shift. I'm going to map a particular vertex v1 or element to the origin. And now notice that the distance between I and j squared, which is this, is vi squared plus vj squared minus 2 vi dot vj. Yes? But vi squared, because I set v1 to be 0, is vi minus v1 squared is equal to di0 squared. This is, and therefore, we have constraints, we can read off that vi dot vj is just 1/2 of d1j squared plus d1i squared minus dij squared. Okay, so this just shows that if I tell you all of the distances between things, that immediately tells you what all the dot products are between different pairs, and vice versa. If you know the dot products, you can compute the distances. So somebody shows up and says, I want you to achieve these distances. I immediately translate it into, I want you to achieve these dot products. How do I create an embedding that achieves a certain collection of dot products? Yes? Exactly, right? So just write the matrix of dot products. And then do a Cholesky decomposition. Which is what we did for the semi-definite program, semi-definite programming problem, right? It's the semi-definite program said, here is your matrix of dot products, give me vectors that achieve those dot products. And that's what the Cholesky decomposition did, okay? You can actually go further, right? With this insight, it turns out that you can also find the minimum distortion embedding into L2. Because that's just SDP. Right? If you want to achieve a certain distortion, that is specifying certain linear constraints on the distances, which turn into linear constraints on the dot products. So you solve the SDP, and you read off the vectors, and that gives you the minimum distortion embedding into L2. Okay. Something else that's kind of interesting is that every metric can be isometrically embedded into L infinity. Okay. And here's how you do it. I'm going to make one coordinate for each element of the starting metric space. And I'm going to define the embedding's x coordinate for u to be the distance from u to that x. This is one of these weird computer science, this makes perfect sense mathematically and is a little hard to wrap your heads around. But essentially, you've got one coordinate or one column for each x, and what you have running down that column is just the distance from x to all of the other points. Okay. Why does this work? Well, if I just look at the difference in x coordinates between 2 points u and v, that's equal to the distance from u to x minus the distance from v to x. No, minus. I'm subtracting distances. Why am I subtracting distances? Well, because by the triangle inequality, this is at most the distance from u to v. Okay. Yes? Then you have a Hilbert space, right? You have an infinite dimensional vector. Okay. This is still true. I mean, it's still true that you can embed it. Okay. So this is the triangle inequality, right? But what that means is that we have a contraction. Right? If each coordinate is less than the distance from u to v, then the max of these quantities is also less than the distance from u to v, so it is a contraction. Yes? But if we look at the coordinate u for v, it's just duv, but coordinate u for u is equal to 0. So their difference is duv, right? So this achieves the max of phi x of u minus phi x of v is equal to duv, which means that it's an isometry. So L infinity is the universal metric. Every metric can be represented isometrically by L infinity. Okay. Okay, now what we are going to do, right? We are going to do our rounding by embedding in the L1 metric. I'm going to give you an algorithm for taking an arbitrary metric and embedding it in an L1 metric. Okay? And the key theorem is that you can do this with order log n distortion. Yes?
Order 1 over log n.
Yes, if like it's like with approximation ratios, right? It's clear if you use a number bigger than 1 or smaller than 1 what you mean, because the approximation only happens in one direction. Okay? So there is a theorem that you can embed into L1 using only order log n distortion. Okay? I want to think about what I can prove in 2 minutes. Yeah, I will prove this next time. Okay? But suppose that we have it. Okay? So suppose that I have an L1, I've embedded my graph in an L1 metric space. Okay? Such that the edge volume, right, sum of edge length, sum of distance between endpoints times capacity of edge, is less than or equal to beta times the total volume, or the total distance of the vertices, right? So there was a ratio in our linear program. We do an embedding. We get new distances, but we can talk about the edge volume and the total distances in this L1 space between the points. Yes? I claim that I can round this to a cut with the same ratio, beta. Okay. And the method is, well, what I sadly erased. Okay. Essentially, we think of each of the dimensions in this Manhattan metric. Remember, L1 is the Manhattan metric. We essentially look at each of the dimensions of the Manhattan metric as a line, right? It's all one direction, right? And in that direction, we use the same rounding idea as we used for ST min-cut, of just marking a particular point on that line in that direction and using that to separate vertices. It's just that we're going to do this on all of the different dimensions at the same time. But just as in the one-dimensional case, we will find that the approximation ratio of this rounding is 1. Okay, and we get exactly the same ratio in our rounded metric as we had in the L1 metric. So the only loss is from taking an arbitrary metric that we got from the LP relaxation and paying a log n distortion to turn it into an L1 metric. And that means we'll have a log n approximation to the optimum ratio. Yes, question? We will see, sorry, what you do is you average over all of them. Okay? Or to put it another way, you pick a random dimension and you put a cut in a random position in that dimension. But that's a good question. Okay? So next time we will analyze that, and I will show you how to do the embedding itself, which is like an important result in mathematics about metric space embeddings. And then we will start on Markov chains, which are the last and very cool topic for this class.